get started. So I have a project right now. It's basically an assignment. It is an assignment for a machine learning course that I'm taking over this summer. One of the primary tasks we have, a machine learning task, is to find and curate our own data set, which is a very open-ended project. The objective, it's in 3 parts. Basically, the first part is to do an exploratory data analysis, with whatever chosen data set that we have. The requirements are it needs to have 100,000 observations, it needs to have 20 individual features, and the primary objective is to get an independent variable or a target variable, which is basically a discrete variable, one that we can do classifications on. So we'll go through and we'll do things like cluster analysis on it. We'll do things like support vector machines on it. So over the course of the summer, the data set that I select, we'll go through the different stages of it. But for the first part is basically just to pick the data set, and then for a little bit here and now, I'll go through some of the work that I've done today on my chosen data set to get it prepared, how I'm building out some more features and some support, support columns and support data sets. I'll go through, between BigQuery, and then I've started using, just briefly, I've started using this tool from JetBrains called DataGrip. And so I got that hooked into my BigQuery project, and so I'll go through and we'll look at how some of those queries are written and saved and formatted. So the data set that I've decided to work with, I actually went through a ton of data sets inside of Google's public BigQuery. I don't actually know if I can zoom in on that. I actually probably can't zoom in on that. There we go. They have public data sets inside of BigQuery that are available. So these are like 311 phone calls, information phone calls in Austin, and bike share data. There's a whole bunch of blockchain and crypto. The Bureau of Labor Statistics, they've got a couple in here, which are like the consumer price index. So if you're interested in inflation, that's all available. Efficiency in terms of employment hours and wages per employment hours. There's a ton of stuff in here. And originally I was considering doing just the American Community Survey from the census. And that's basically a survey that gets sent out each year, and they have a 5-year, a 3-year, and a 1-year estimate. And the sample size, for 5 years is large enough to go down to what they call census block groups. Huge amount of information inside of that. Really, really interesting stuff. But the more I got into it, the more I found, not the data set, but the assignment, that there were actual restrictions that we couldn't do anything that came from Kaggle. And Census Bureau data in the U.S. has kind of been done ad nauseum inside of Kaggle. So there was, you've got a whole bunch of crime databases. I wanted to avoid those, namely because I didn't want to do any social science research or filtering on any of the the results that come out. I think that's probably pretty self-explanatory. I'm not a social scientist. I'm not paired with a social scientist. I think it's probably problematic for individuals to go out and to analyze data sets that have social implications inside of them without someone sitting next to them working on what the implications are and things like that. So obviously there's a whole bunch of data inside of there. The ones that I mainly considered, I was going to do an FDIC analysis for bank openings and closures. That one didn't have enough feature columns inside of it. I was going to do an FDA drug list and formulary list analysis potentially. That one, we have a restriction that we can't use image data, and we can't use text data, and we can't use sequence data. So basically, nothing inside of that data would have worked. I started looking at some of the NASA data sets with the TESS program that's going on right now, which is the exoplanet survey. Unfortunately, all of those come in as sequences of infrared images, essentially, and so those are basically the only data set you would have would just be rows of infrared pixels, basically, and so that fell outside the bounds of the assignment. What else did we look at? Regardless, what I ended up with, and it's been years since I've done it, played it, but I ended up with a baseball data set. And inside of BigQuery, they have this baseball data set, which is published by Sports Radar. I think I got that right. Sport Radar. And this is the full play-by-play data set from 2016. They have the regular season games in here. They have the postseason games in here. There's a schedules data set, but all of this is flattened. They call this data set wide because it's a wide data set. It has all the information from the schedules inside of it. And when you go through the list of all the information that's available, obviously a lot of it is not going to be used outright. In the exploratory data analysis or in the final data analysis, but there's enough in here to be able to kind of create some hybrid features. And with that, the hybrid features that I'll come up with, or the calculated features, or the derived features that I'll end up producing, are going to be way more than 20. We'll have plenty of features inside of it. But then the question becomes, inside of the game of baseball, what exactly would the independent variable be? And as I've titled in the stream, what I think I'm going to try to do is to predict what the next pitch is going to be, and I'm going to treat that as a classification problem. And what's really interesting with the Sport Radar API, the pitch types is one thing that we can and I just need to zoom back down here so that we can make sure that we stay on the right thing. Their website is a little it's a little iffy. Pitch type is one thing that I can predict. So based on the state of the game up until now, and based on the state of the player up until now, before the pitch is thrown, using that information, can we classify what this pitch's type is going to be? And so, is it a fastball, sinker, cutter? These are all basically just movement on the ball. And then there are also, there's some other interesting stats that get tracked inside of this, which are, we also get the pitch location. And these are discretized into the strike zone. And so they have individual IDs associated with each one of these. Every pitch is classified inside of one of these zones. And these zones are from the pitcher's perspective. And so depending on whether you have a right-handed or a left-handed batter, you have, inside, outside balls, high ball, low ball, and then there's a zero. I believe zero stands for in the dirt in this particular data set. But then your strike zone is delineated into nine zones inside of that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So on top of being able to predict what the pitch type is, we can also, if that doesn't work, we can try to pick what zone it's going to be. And if both of those do work, then you can essentially have a location and a movement or a type predictor. And on top of that, the third one that we have available to us, which is a continuous, let me find that, pitch speed. So we also then have how fast the ball came into the strike zone. And so that's a third one that is measured right now in miles per hour. So obviously that's a continuous variable, not a categorical variable. But it shouldn't be too difficult with a little bit of data analysis and exploration to come up with ways of quantizing that or discretizing that into relevant speed ranges, and essentially trying then to predict what the speed is going to be. What's important though is that any characteristics of the pitch itself are somewhat all correlated with one another. So if you're throwing a change up, it's going to impact your speed. If you're throwing a slider, it's going to show it's going to change or increase the likelihood, or be correlated with where in the pitch zone you end up, depending on again whether it's a right-handed, left-handed batter. So all of the pitch characteristics, all of the measurements we have about the pitch from this data set, those are kind of going to be fair game as variables we're going to try to predict. And then everything else that we have access to is going to be fair game for us to create as features. And so just real quick tonight, I'm going to go through what the original data set looks like, the structure of it, what I got out, what I've basically just simply decided is not going to be included. And then I'm going to go through a couple of transformations. And I just want to make sure that between my two windows, I've got the right data sets up. Let me clear that. And here we are. And here's that. Oh yeah, I had also, this foods data set is still out here. I'm going to actually go ahead and get rid of that one. This one is out there. I'm going to make sure that there's nothing in there. Okay, good. I was thinking about nutritional labels. I was going to try to do classification on nutrition labels. But anyway, so I'm going to get rid of that so I'm not confused. There we go. And so I'm going to start first with this play-by-play data set. So this was me going through, and there's not really a whole lot of cleaning that has to be done with the data set. Thankfully, it's pretty well organized, and I haven't really done any aggregate statistics yet. I haven't done any descriptive statistics yet to see, what we're dealing with in terms of my beliefs on the overall accuracy of the data set itself. But in general, it seems to be pretty well structured, and there don't seem to be too many observations that are, that are just like completely out of what I would have expected from a schema and from a format standpoint. This games wide is going to be the primary source, so that'll be the system of record, and then inside of that data set is about 2 gigs. A little less than 2 gigs, and it's got 761,000 individual records inside of it. And this data set, each row or each one of those individual records, those are essentially pitches. We have a couple other events inside of that table, which are essentially lineup changes. So for some reason, when they were materializing the data set, you'll notice, their data set has all of these tables and APIs inside of it. When they were materializing that and flattening that down into a single view, they decided to keep lineup changes inside of that as well. So kind of the first pass I do is go through and get rid of that information. But all of this is already oriented pitch by pitch by pitch. And so, yeah, it was kind of fun. I got a little bit more done today than I thought I was going to. Once I had picked that particular data set. So, what we start with their data set has game ID as season ID, and I'll actually go into the preview view so we can see what the data looks like. They've got a GUID for their game ID, and the season ID tells you it's a regular season. what year it is. They have the start time of the game. All of these are in UTC, so that already helps with dealing with time zones for game starts. They have the attendance at the game, whether it was a day or night. They have the hour duration and the minute duration. They have the teams, and then they've already essentially grouped, they've already merged to get the team names associated with it. You have the individual venue. You have the venue surface. So this is one that I will include. We have the capacity for the venue, so you can get the fill rate basically of the stadium as attendance divided by the overall capacity. So you know whether it's a popular game or not. We have the city, the state, the zip. Those are less significant once you already tie it to the specific team itself, because those don't really change. But interesting information to have. They have the venue distances. So I thought about including the individual distances of the venues, but again, these aren't going to change outside of having the venue itself. And so, venue pretty much already encodes all of that information, since we're not going to do anything fancy with trying to do where the ball was hit. Since these are just pitches, we don't really have to worry about that. And so I'll pause for a second, and I'll also reference inside of the data set, and this is really cool, and I'm going to include this as part of the exploratory data analysis report itself, but they also group the field into zones, and you have the outcome of every basically contact. And anytime the bat makes contact with the ball, you have information about which zone that it went into as well, including the status of it. So that's a whole other set of exploration. You can imagine that the dimensions of the field would change the likelihood of ending up in one zone versus another. But since we're only focusing on the pitches, these outfield distances are not as significant for us to take a look at. You have the basically the final box score is included for both home and away, so that has runs, hits, errors, and then you have the result for each of the individual innings. Those are less significant for me for what I'm trying to predict. Those are nice to have aggregations if you need them, but we're basically going to go through and build those from scratch. And then we have information about the individual innings. So you have the inning number, whether it's the top or the bottom. We have the event type itself. And then we have what's called the inning half event sequence number. So this is basically which at-bat number within the inning are we at. And you'll notice that, like everything in BigQuery, there's no guarantee or there's no requirement for ordering or sorting or anything like that. So these are all coming in out of order to begin with. For the most part, you may occasionally run up with some records that are next to each other. And actually it looks like that one. Oh, that's interesting. So I haven't done anything with the text description because we're not going to use text description, but it looks like they take the description for the final event, because this was the sequence number 3. This was the third pitch. And it looks like they take that result and they move it backwards. So they backfill some of these, which is interesting. We also inside of here have a couple events which are steals. So this is when a base runner moves to another base in between pitches, and so those come inside of our event stream. We just clear those out. Those aren't things that we're necessarily going to take into consideration. But I will have a set of data that's included for where the runners are at any given point in time. So I'll talk about the state transition and what pre-pitch is, during pitch, and then post-pitch, and how we shift those things forwards and backwards to make sure that we're getting, the right amount of information that would be available at the time we need to predict what the next pitch would be. But we'll clear these steals out once we start doing the actual data set itself. You have the time that the individual play happened. I haven't yet, but I might consider trying to get the time in between pitches or the time in between these individual events. But it does strike me, no pun intended, those strike me as things that aren't necessarily, those are directly controlled by the pitcher, and so I would consider that not necessarily to be an input, but kind of like a quasi-predicted timing as well. So, based on the state that we're at, is the pitcher rushing? Is the pitcher slowing down? That seems like that's an outcome and a behavior that the pitcher actually has control over, not an input. That feels like it's not an output. That feels like it's an independent variable, not a dependent. In some instance, it feels like it's a dependent variable for the pitcher, and or a dependent variable. I don't know. It could be on either side of the equation, basically, right? So I don't know. More to come on that one. It's in there, but I haven't really figured out exactly where to put it. Whether it's an input that the pitcher has, maybe total time so far for the at bat, or whether it's an input that the batter essentially would have in rushing them or things like that. These outcome. This is basically what we're keeping track of for the state machine that is everybody on the field knowing what's going on. And so all the outcomes, they have a first letter, which is one of 4 characters. It's a K or a B. So K is for a strike, a B is for a ball. So K means it was thrown in the strike zone, B means it was thrown outside of the strike zone. Then we have A for the batter advances to a base, and then we have an O for the batter is out. It is possible for a runner the batter to advance, a runner to an advance, simultaneously. Like, let's say somebody's on first and the batter hits a single, then the person on first advances and the batter advances, but then let's say the person running to second decides they're going to run to third, so it becomes a fielder's choice at that point, and they get thrown out. I think it's a fielder's choice. I don't know exactly how that would have been scored, but all of that information essentially gets captured inside of these outcomes. Let me see if I'm going to try to find the list of those. So AHR. Here we go. So these are all the possible pitch outcomes with their nomenclature that goes on top of it. So this was a hit, it was a double, but then they advanced to third. So this was a hit, it was a double, but then they advanced home. This was a hit, it was a fielder's choice, and then because they messed up the fielder's choice, they ended up advancing to second. Again, the way this plays out for things that are that specific in terms of the ordering, I think that could be, in order for it to be a fielder's choice, I think the ball has to be in play. And then it seems like the ball goes into play, and then maybe somebody was on second, or maybe somebody was on first and tries to go to third and gets thrown out on third. But then while that's happening, the batter themselves is then able to advance to second. But anyway, we're not going to get into the super nitty gritty outcome of any of these per se. But I have collected the two parts of it so that we know the general code for what happened and then we know the detail for what happened. There might be differences in what a pitcher is going to throw based on, whether it was an error or whether, there was a bunt that just happened. I think a lot of that ends up encoded in which runners are on which bases. But that's all there. So if you go out and you want to work with the data set, you can try to do something with it. I might come back and do something with it. It turns out over this entire data set, despite all of these codes that they have available, there are only 48 that get used, and like almost 98 or 99% of them are like the top 5. So yeah. Then we get into the hitter statistics or the hitter information. So you've got a GUID associated with the specific hitter. You've got their last name, first name. You've got their weight in pounds. You've got their height in inches. You've got their handedness. Are they a right-handed hitter or a left-handed hitter? Then we go into the pitcher. Each pitcher has its own, GUID. They have their first name. They have their last name. Are they throwing right? And then these are what we're basically going to try to predict. The pitch type is one predictor. So this was a slider, a sinker, a cutter. They go ahead and they include the description in this data set, but that's superfluous. We have, not superfluous, sorry, that's extra. That's not needed. We have the pitch speed in miles per hour, and then that's where the zone information comes for the individual pitch. We also have information about what this individual pitcher's pitch count is, and those are traditionally counted throughout the game. I will maybe in a later one, a later video, I'll show it. I'm gonna create a couple different rolling pitcher counts. So over the season, how far are we? Over the last 5 games, how many have we had? Maybe not 5 games because that rotation is probably longer. Maybe over the last 10 games or whatnot. I want to keep multiple different versions as input variables for what the rolling pitch count is. You have the hitter pitch count. This looks like it's pretty much the exact same as the sequence number inside the particular at bat. But hey, you never know. There might be somewhere where that grows differently. The hit location is again on the field. Which zone do we end up on the field? We have a hit type. There are 4 of them. There's a fly ball. There's a line drive. There's a pop-up. And then there's a grounder. So those are the 4 types. And then at each pitch, you have basically the pre-state of the count. So how many balls do we have, how many strikes do we have, and how many outs do we have? And then afterwards, after this particular pitch, how many strikes do we have, how many outs do we have? This needs to change in our actual final data set, and I've done some modifications to that, and I'll show kind of what those look like. But yeah, so that's the count, and then we move into the runner on base. So the most you can have are 4 at any given point in time. So there are 4 different sets of runner on base 0. So that's one runner on base 1. That's another one. Runner on base 2. That's another one. 3 and 4, and those are grouped together into 5 different variables. So runner on base 3 starts as, and then this is the player. So what player is currently in the runner on base 3 position? Where do they end? So if they end on third base, that's where they ended. If they end on 4th, that means they scored. And you see here the outcome ID for that was an earned run. This was an earned run. This was an earned run. So my guess is that was probably... those probably came from different games and different data sets, actually. If it would have been a home run, you would have expected there to be not 3 in a row vertically, but you would expect there to be 4 in a row horizontally. You would have expected 0 to have made it home, 1 to have made it home, 2 to have made it home, 3 to have made it home on the same pitch with the same outcome. Excuse me. There are a couple flags then after this, which are, just, I guess, like some sugar data that's been thrown in. The idea of whether or not this counts as an at-bat, whether the at-bat is now over, whether this pitch counts as a hit, whether it's an on-base, whether it's a bunt, whether the bunt was shown, was there a double play, was there a triple play, was there a wild pitch, and then was there a passed ball. These are, if you were to try to take this data set and go off and recreate individual player statistics over the season, you would need that type of information in order to get on-base percentage. You would need that information to get batting averages. So those are added flags for, like the back of a baseball card type stats. But we won't necessarily need those because we're not concerned per se with any of that information in my current thinking. Maybe a pitcher changes what they're gonna throw based on whether there's a double play or a triple play on the previous pitch, but in my thinking, that will all get encoded essentially within which runners are on which bases, and so you would go back to nothing. If it's a triple play, obviously the inning is over and that wouldn't matter. If you go to if you get a double play, then you had whatever, 1 on and none, or 2 on and 1. But anyway, so I've currently ignored that for now. And then they have information about which fielders are present in each of the positions. I don't know what fielder 10, 11, and 12 are. So you would have 9 positions typically. I don't know what 10, 11, and 12 would be. Anyway, and then you have essentially the lineup, which is the order for the batter 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have home fielder, home batter. And then if it's a lineup change, they have the lineup position that the player is going into, and then where in the lineup they go and what has changed. So like this is an example of a change, and they are going, that's a pitcher, that's a relief. The position, I think, yeah, so that lineup position versus lineup order. This is a pitcher who gets placed in, and there's a DL, so they're not in the lineup. That's how I would interpret and read that particular row of data. Cool. So that's the data set itself. I'm gonna switch to data grip and explain what I did with it for the first calculation of this play-by-play data set. So this is the one that I have created and I've basically materialized. This one has 716,000 records in it, and I was able to get it down to about 260 megabytes. So the information the data size as they originally had it, there's a lot of duplicate information in here because it is a wide data set. If you think about those GUID fields, those are, I don't know the exact size of them. It looks like they're integers, so that would be, I think the default is a 64-bit integer in BigQuery. Let me find these IDs, or they're strings. So those are relatively large. And then I also got rid of some of the records like steals, and I got rid of records like the steals are gone, and lineup changes. Those are taken care of as well. And so we end up reducing by about 50,000 records, and we end up reducing the size by whatever that is, 1.5 gigs. Yeah. And so then this play-by-play becomes the basis for all the rest of the data sets that I'll be building off of it. And then once I get the individual fact tables or the event tables compiled, then I will merge all of those together into the single data set that we'll use for the actual project itself. There's another, as there always is, there's another set of requirements for the academic part of the project, where we have to use R to do all of the exploratory and, basically any of the analysis itself outside of the data prep side should be done in R. So I'm just using BigQuery because I'm used to it, and it's faster for me to write some of these queries. So anyway, that's why we're here, and then once we're done, it'll merge together into probably just a nice little CSV file, and we'll go on our way with the actual prediction tasks. So let me switch to data grip. There we go. And inside of data grip, hopefully it's visible. I apologize. I'm getting over some illness over the last couple of days. I don't have a vocal modifier on. It's just day 4 of a sinus infection basically. So first and foremost, I take the game ID as the game ID. We're not gonna mess with that. I do prefer using underscores when I'm dealing with anything that's a table. I really don't like camel case personally, but obviously that's because I come from mainly a Python background when it comes to analyzing data sets and things like that. So we start with the game ID for the play-by-play, and then I created a hash of 4 fields that seem to provide a one-to-one cardinality for each row, and so that becomes the row ID itself. So that's the game ID. Created at is a date time variable, so that's when this individual record itself was created. I pull the event type in. I don't really need the event type because I've cleaned all the rest of them out. But that's a legacy left in there for the calculation of the MD5. And then if I decide to add other events back in, I just want to make sure that I don't have to redo all of my game IDs and things like that. Or sorry, all of my row IDs. And then it's also specific to the individual hitter. There are some instances where I don't know why. I think there are like 6 or 7 occurrences where we have duplicates to the row ID if we don't include the hitter ID. And those are so small, normally I would get in and I would investigate and try to figure out why that is. But these are small enough where, as a percent of the overall number of records, that I don't really care about it that much. But this little snippet, this is how we create what will later eventually become the join field for our individual records. The other reason I'm using MD5 for this and not just the fields themselves is in the event that I need to or want to do partition joins. It's pretty easy to just partition by the first couple of bits in the or bytes, depending on which function you use and which type you use to do the join itself. You can just pull off and essentially bucket based on the MD5 before you go through and do the merges themselves. So that's also why I'm combining those fields into a single record for the row ID. And then also, last on that, when you do those partitioned joins, the MD5 will essentially be a random number associated with that, so you shouldn't run into too many hot keys or hot partitions when you try to do those joins. Home team name comes in as the team's home, team's away. When it comes to dates, the start time is a timestamp, so I serialize that into a string for taking out the date component. We have the year, the month, the day. That's the start date, start date. I also pull the timeout, so these are UTC, so date start UTC. And then I have the duration, so I go ahead and put the end time in for the game itself, and that's date end UTC. I don't really know if there's a reason for that. There might be a reason, we might need that in the future, or overlaps, or maybe there's something significant about ones that last longer versus not. I don't know, but that's just included in there, kind of a just in case while I'm in the early phases. I also am collecting information about the venue. So the venue name, what its surface is, its size, and whether it's a day or a night. And I've included this _E at the end of it to just let me know that that's an ENU. Yeah. This is the fill rate, so we take the attendance divided by the capacity multiplied by 100, round it, and then turn it into an int. That gives me the fill rate, so 41% is represented basically as the number 41. And then we have the duration in minutes. There's some work that can be done inside of that to figure out the timing and the pacing of the game and whatnot, but I think for an assignment it'll probably be fine to just ignore that, or use that as a factor for maybe we lag that one and it's how long was the last game or whatever, but that's there just in case we need it. These are how we do our orderings. So we have the inning number, and then if it's the top, I give it a 0. If it's the bottom of the inning, I give it a 1, and that's just so that it lexicographically sorts correctly. Otherwise, it would be B versus T, and so it would sort in the opposite order of how they came up. And so if you're not familiar with baseball, the away team bats first, and then the home team bats. So we call that the top of the inning with the away team, and then the bottom of the inning is the home team. In their data set, we have this inning half event sequence number. This is then within the inning half, which at bat are we at, and that increases for each batter we're seeing. And then the sequence inside of that at bat increases by 1, and this is basically the pitch count inside each at bat. And so I've named these so that you can see the hierarchical nature of those. And then anytime we want to create a time series or create an ordered set of pitches or an ordered set of events, recreating kind of what the play-by-play was, you just sort by the game ID, and then you can sort by the inning number, the half at bat, and then the half at bat pitch. Next, I have a set of information about the batter. So you have your hitter ID. I prefer batter. I don't know why. So I've just named all of these batter. So there's the batter ID, their name, their weight, their height, and then what hand they are, their handedness. And then the same thing for the pitcher. So the pitcher ID, the pitcher name is just concatenated last name, first name, and then we have their handedness for their throwing hand. Then there are three states, and the states are in time, because I'm envisioning at the very end you're able to essentially use a bunch of drop downs, and you can set up as if you are a batter. This is the state of the game right now, and then what is, the probability, or predict what the next pitch type is going to be, or predict what the next speed is going to be, or predict what the zone is going to be, and then in order to do that, I have to separate things as being pre-pitch on these individual records, because again, this record mixes things that happened before with the pitch itself, with the outcome of the pitch, or things that happen afterwards with the runners. And so I'm just mentally trying to, keep these things in the right spot so that when it comes time to merge everything back together, we're able to create a meaningful data set with the correct order of state, so that, it's usable and we're not, shifting the entire analysis, down by one, basically. So we have the starting balls, the starting strikes, the starting outs. This is what I call the pre-count. And then the pitch count is always going to be 1 minus, because I'm trying to do, this is before the pitch. So we shift all of that information back by 1 right off the bat. And this was easier. I didn't think about doing this until I saw what this output table looked like the first couple of times, but when I looked at it, it was easier to just move this entire field, every pitch, back by 1, and that gives you the pre-count pitch count. Then we get into basically what we're predicting. So this is the pitch type, pitch speed, pitch zone, and then I have I'm going to zoom out a little bit so we can see it, and then now we have the outcome related. So converting the first character of the outcome ID into an uppercase character. And then if there are more characters, then we're going to take the rest of it. And this should actually probably be that -1. BigQuery is very forgiving. So that was technically trying to read too many characters. But it still works. And then otherwise there's none. There's no detail. And so this is outcome code, outcome detail. The hit type is an outcome, right? If they hit it, that's an outcome. So there's an outcome hit type, and then if there's a hit location, then it's an outcome hit location. And so you'll see all of those have names as outcomes. I'm a pretty big stickler when it comes to, particularly when you try to do preliminary data prep inside of SQL, regardless of what system you're in. Trying to keep things named correctly, trying to keep things organized so you can get in and see what they look like. Very, very quickly find out, which section you're in and what things are named and things like that. It makes it easier to come back to your code after the fact. And then these are all the after play metrics, and these are all named as runners because these are related to the runners on base. And what I've done is I've basically collapsed all of the 4 possible on-base runners. On base 0, on base 1, on base 2, on base 3. If they end up on first base, or this one ends up on first base, or this one ends up on first base, or this one ends up on first base, then we give that a flag of true, and otherwise we give it a flag of false. Same thing. If this ends up on second, or this ends up on second, or this ends up on second, or this ends up on second, then we have a runner on second. And then same thing for third, all the way across the board. I'll pause there to say the data governance, whether this should be a 0 or a 1 or a true or a false. It really annoys me when different companies are not consistent in how they do this. I had a prior company that was very bad about being consistent with whether we treated things as bools or whether we treated things as integers in the actual schemas themselves. And then the other thing you'll notice is that up here I have like the word count versus, do I have another one somewhere else? No, good. You'll actually see this. You'll see this play out where if it's a raw metric, then I usually write the full name count for it. Or if, in this case, it's not a percent, it's actually a rate. So I call it a rate there. But then if they are compiled or pre-aggregated, this will be like CNT. So anytime it's an event, it gets called an event. If it's a count, it gets called a count at the end. Suffixes and things like that let me know basically how to interpret or how to use the individual column. This is one that I don't know. I for whatever reason I just wrote it as true and false, and I guess do as I say, not as I do. Anyway. Here's where we filter out outcomes that don't matter. So the outcome ID, if it's a dash in the original data set, that means it was a steal, basically. And then I'm only going to keep the at-bats. I guess in this case, since I was only keeping the at-bat, no steals are in there, so this dash must mean something else in that. But I got rid of them because there was no usable information inside of it. And when I double checked the pitch count up here, when I look at the actual pitcher pitch count in the original data set, it stays constant. It doesn't increment by one whenever you have that little dash there. So something else was going on there. So I just go ahead and exclude all of those. And then this is one where, since this is essentially like an ETL, since this is building my very first system of record table with the play-by-play, I go ahead and I materialize it with this order on it. This is ordering by the start date. It's ordering it then by the time. It's ordering by the number for the inning, for the half of the inning, for the at-bat, and then the pitch inside of the at-bat. This is not strictly necessary. This is a small enough data set where running this order is not, cost prohibitive, not processing prohibitive. So anyway, that's there. And since it's the first table that I run, that has to be executed that way. It doesn't have to be, sorry. In my mind, so I can double check and look at it at the end, it has to be executed with the order on it, so that I have a reference to go back and not keep reprocessing the original data set so many times, since that was gigs at a time. So if we go back to then what the result of that query is, I'm going to reset this to 100, and then we are going to switch back. There we go. So this is that play-by-play data set, and if I preview it, this is basically what it looks like, and it's all sorted and it's nice and cleaned up, and it looks like the very first game was Pirates Cardinals, and that was April 3rd, 2016. Started at 12:05. PNC Park, grass, venue size. You see the game day or night E, the enum for that, and it's day. We have the game fill rate. So as expected, they actually sold more seats than they had capacity for. That's not uncommon in baseball reporting. You have your duration, then you have your inning number, your half. And so again, 0 is top, 1 is bottom. You have your at-bats. And then pitches. So this was Matt Carpenter. He was a leadoff. He had 2 pitches. Thomas Pham, don't know who that is. Which is, it's crazy. I spent however many years in St. Louis. And this would have been, 2016 would have been about a year after I moved back to Chicago at that point. But yeah, I have no idea who that is. I know who Matt Holliday is. But yeah, some of them, anyway. So, and then, Holliday had 6 pitches. And it looks like all 3 of them got out, because then we go to the next. First 2 pitches to John Jasso. Then you have Andrew McCutcheon, 4 pitches. David Freese. This confused me because I thought that Freese was a Cardinal, but maybe he was, and then he wasn't. I don't know. But anyway, then you have your individual pitchers. So that checks out. That works. You got the same batter weight, batter height, and then their handedness. And then these are the count. And so at the beginning, we start with 0-0. Obviously, the first pitch must have been a ball. And you see that the pre-count, the pitch count, so this is the pitcher's pitch count, that is going up until 8. So this would have been the 9th pitch. And then we pick up with the 9th pitch here. So whoever, Liriano picks up again at the 9th pitch. So that all seems like it's going well. You have your pitch types. So obviously, starting the season, first game, first pitch, 90-mile-an-hour fastball. Pitch zone 11. Let's see where 11 is on our little pitch zone reference. 11, I think that must have been inside, probably. I lost it. 11. Yep. And so it was a ball. The next one was a fastball. This was a 4, so that was probably in the strike zone. Yep, 4, so it went opposite side. And then that was a ground out. That was a ground ball. It was hit into location 24. So we come back over here, 24. It was hit to the first baseman. No runners on. Then basically the same thing happens on the next. So Tom Pham, ground ball to 25. Where's 25? So this was a nice little short one, probably either the shortstop or the third baseman. Yeah. And so I'm just going to double check, and I'm going to go to ESPN MLB 2016. I think we can do play-by-plays inside of here. I think this is probably weird, or I don't know. Twitch might not like me going through other external sites. I don't know. But let me find. Let me find the Cardinals. I'm going to go to the schedule. We're going to go back to 2016. We're going to go to the first half. April 3rd. There's the game ID that I'm looking for. There we go. And then if I go to the play-by-play, there we go. So the first was a ball, and it was inside. Then it was a ground out, and he grounded out to first. There we go. Pham grounded out to third. And then Holiday struck out looking. So if I go to this next one, if I go back, my poor computer has too many things open. If we go back into this, then we see there's this strike looking, ball. Yep, ball. Foul ball. strike looking, strike looking. That should be all three. That should be a strikeout looking. Foul ball, strike looking. Yep. And there we go. So our individual play-by-play works. We've got the data that we're looking for. That process is good. Now I say that having checked only like 3 games, but for a class, for school, I don't think there's any reason to consider having to go through and to spot check more than a couple. So I'm gonna take a quick break. My computer, I gotta close some stuff, and then I'll show real quick a couple minutes on the next data set, which is this batter events calculation. I'll show the query for how to get this and how to do these sequences and how it does running counts for each of the individual pitches. But yeah, then we'll wrap up, and I'll work on probably in the next couple of days I'll work on getting the pitching events ready to go, and then we'll merge everything together and look at what the final data set looks like. So I'll be back in a couple minutes. right. I didn't realize how late it was. So I'm gonna go through the batter events. I'll go through the code for that real quick. And it's fairly straightforward. I'm gonna close some windows as well. We'll see if we can get some performance back. I don't think I'm gonna need a couple of these. And yeah, so let me go back to the IDE. So this is the batter events table. And so at first we start off with basically just a base table, which is the batter's view of events. We're going to select initially from this play-by-play. And when I first did this, I selected only from a test, basically a subset. The subset had, I think, like 20,000 records in it when I first started building it. We pull in the game ID, the row ID. We pull in everything necessary for the starts. We have the batter ID, and then the sequence, the hierarchy of the sequences there. So the inning number, the half, the at-bat, the outcome code, the outcome detail. And then this is where I begin to transpose the individual outcome codes into numeric events. So for this particular pitch was the outcome a K event, a B event, an A event, or an O event. K and B are mutually exclusive of A and O, or I should say K or B are mutually exclusive of A or O. Again, K is a strike, B is a ball, A is a batter advances, and O is an out. And once we have basically this preliminary projection, which is basically just a named subquery, then we go through and I pull in the actual information itself for what the final table is going to look like. So we've got the row ID, the batter ID. I actually want all of that information. So we start, the first set are basically all the identifiers that we need. Then I pull in individual pitch level data. And then if you think about what I'm trying to do here with this batter events, I'm trying to make it so that I can join whatever future tables that I have using that row ID. And that row ID needs to capture all of the previous information up to this point, which is basically trying to compress a sequence into a single observation. And so obviously the outcome of a particular pitch can't be used to determine or predict or classify what the pitch type is or the speed or anything like that. It might be a predictor for it, but what I'm trying to do with the data set, or what I'm trying to do with the application of it, is to predict before we have that information available to us. So what I need to do is I need to create these windows and these aggregates. And so there are, from a batter's perspective, there are 3 types of windows that I've created. So I want to know, in this current game, start a counter of all of these events and cumulatively sum everything as we go through it. I also, batter by batter across games, I want to know their last 50 pitches. So start that counter, and then once we get to 50 pitches, move that window forward pitch by pitch by pitch every time they have a pitch at bat. And then the third one is kind of an overall aggregate. How's their season going so far? And so that's like taking the last 50 pitches, but instead setting it to be the last infinite number of pitches, or season level, since there's only one season worth of data inside this particular table. And when you organize it this way, it's incredibly simple. This looks very, very, very straightforward. So before I go through what the calculations are, I want to go through what these windows are. BigQuery allows you to essentially create named windows. And within these named windows, you can partition and you can order, and then you can specify within that window which rows count. And so a game window versus a season window versus the last 50 window, those look like the following. Within the game, I partition, so I look and essentially I group this calculation only by the batter ID as well as by the game ID. I order then by what inning number am I, what is the at-bat number that I'm at within the inning half, and then what is the at-bat pitch. And this is just to make sure that we're sequencing these things in the correct order in time for when we then go and pick which rows qualify for our what we will turn into a rolling sum. And so the rows for a game window, we will include with this partition, so filtering by that, for each one of these, ordered by these, we will take unbounded preceding rows, so all the way back to the beginning, as many rows as you have, up to one row before this. And so this basically just flattens all of the history. And depending on what aggregating function you use, so like a sum or the variance or any function that you put inside of there, this chooses which of those rows and the order that those rows should be considered. And that's what the game window is. The season window, we basically do the exact same thing, except we no longer need the game ID. So I'm not going to partition by the game ID, but since I'm not partitioning by the game ID, I now have to order by when those games occurred. And so we add a date start date and a date start UTC inside of the order by clause. And the rows are going to be the same. Unbounded preceding, so everything you've got from the beginning up to the most recent one that I have, so the one just before where I'm at. And this will essentially compress an entire season across whatever aggregating function that I have into a single window for that. And then lastly, similar to the season where it takes everything, the last 50, instead of doing an unbounded preceding like we did here, I've just done 50 preceding here and 1 preceding there. As I look at that, technically, I guess that should have been 51 preceding. This is, I guess, technically only has 49 inside of it, I think. I'm not actually sure if the between is inclusive or exclusive. I think it's probably inclusive because it's a between. So my 1 versus 0 indexing is not great, I guess. So I don't know if that's 49 or if that's 50. But that's how those 3 windows are calculated. And then using those windows, I am essentially summing up how many strikes over that game window has this individual batter had. How many balls over this window has that batter had? How many advances and how many outs? And what the coalesce is doing is saying, if I don't get a value, and really the only time I won't get a value is if I have no prior rows, or essentially if this is the very first at-bat of a game, or if it's the very first at-bat of a 50-pitch window, like the beginning of the season. Those are the only 2 instances where that might come back with a null value. But to just simplify it, you wrap it in a coalesce, and it says, if this is null, give me a 0. Otherwise, give me that first value. It resolves from left to right. Now, those individual rolling sums, again, I said the strikes and balls are mutually exclusive of advances and outs. And so because of that, we have two different sets of denominators. And the denominator for the strikes and the balls gets assigned to the denominator count for the strikes and balls. And the denominator count for the outs and advances gets assigned to that game AO denom count. So we're basically doing the same thing then 3 different times. One for the game level, one for the last 50 pitches seen, and then one for the season overall. And that's it. And that's all you got to do. What this produces then, I'll switch one more time. So this one still has the 20,000 inside of it. I need to rewrite this with all of them. But beyond that, the data set itself has the row ID, it's got the batter ID, it's got the inning number, the half at bat, the at bat pitch. It has all of the individual events. So these are the results from this particular this particular pitch's result. And then so far, for that pitch up until there, this game has seen 4 strikes. They saw 4 balls. There was 1 advance and there was 1 out for a total of 10 pitches, right? So between the two, we've had 10 pitches up to that point. And now we can start doing something like, we know since those are mutually exclusive, every at-bat is going to end with an A or an O. And so at this point, to this pitch, before leading up to that particular pitch, the row that this is associated with, this row ID, leading up to that, this person was basically batting 500. There was 1 advance and there was 1 out. Same thing for over the last 50 and then over the last, over the entire season. And so what I'll do is we'll grab one of these batters and we'll show that this actually works. So let me zoom in here. So we're going to do select star from ML Summer, and then I'll go ahead and I'll do the batter events. So we'll do that first. So that gives me what we just had. Row ID, batter ID, inning number, half at bat. And I haven't included enough in here to do this exactly, but what I could do, so it's hard for me to get this back to a sorted data set because I haven't included the information that I need in this particular table without doing another join. What I can do is so here I'm doing an inner join on the row IDs. And here I'm going to pull in the game ID. And here I will pull in was it, date? There we go. Date, start, date. PvP, date, start, UTC, which is the time. Technically you could do, inside of the join clause itself. This is actually written pretty terribly in terms of an optimization. So I'm just going to leave it like that. B.row batter ID. We're going to sort by date, start, date. PvP, date, start, UTC. And then be.inning number. be.inning half. be.inning half at bat. be.inning half at bat pitch. And I believe that will order everything correctly, and it's going to give me everything from the original BE data set. And then we'll have this limited to just this particular batter. And just so I can see at the end who this is, I'm going to add the batter name. All right, 6 megs, cool. And then I'll go ahead and run it. I'm going to shrink that over. So out of curiosity, okay, so this is Matt Duffy. And if we look at the order of what's happening, so this is in the same game. There was an at-bat. He came up third in the second inning. Came up seventh in the third inning. Had 1, 2, 3, 4, 5 pitches in the third inning. And then if you look at the individual events, so this was an out, which makes sense because that was it. There wasn't another event in that inning, half, or the at-bat. Then we moved to the next one. There was a strike. Then there was a strike. Then there was a ball. There was a ball. And then this was a strikeout. Then we moved to the next one. We have a ball, we have a ball, we have a strike, then we have some type of a hit, there was an A. And so right off the bat, the question becomes, if there's an O, what happens if they strike out, right? So if they strike out, does that become an O event or does that become an A event? What I need to do is I need to write in some more logic which calculates and updates the event O if this is the third strike. And we have that data in the original table. So it will look at whether this pitch is the third strike or not. And if the pitch is the third strike, then we go ahead and we flag the event O as well. In that case, those wouldn't be mutually exclusive. So I might need to add that as like a third type of mutually exclusive set of events. But if you look at what the windows were doing, this is accurately calculating at this field or at this pitch, there had been one strike. At this field, there had been 2 strikes. This field's still 2 strikes. It was not a strike, not a strike. Then we get another one, so that updates here to a 3. Then we get another one, and it updates to a 4. And you see how these are growing across the individual at-bats. And then with the balls, 1 ball, 2, 2, 3, 4. the first out, we started at a 0, but then it goes to a 1 and a 1 and a 1. Yeah. And I believe we might have more than one game available here. Yep, so this goes to the next, this row 20, goes to the next game. And we see that our game counter restarts. So it goes back to 0, goes back to 0. Our last 50 continues to grow. And since that was 20, that last 50 obviously will increase. If I go down to, let's go to the next set, the 50 is still saying relatively close to this 20 number. You'll see that it grows, right, until we get to the 51st, and it is increasing, but it's not increasing the same, monotonic, incrementing by 1 that something like the season will do. And the season count just always continues to increase over time. And so we see by, the 91st pitch, we've crossed multiple games, but the season count, there have been 38 strikes to Matt Duffy, 32 balls, there have been 4 hits, and there have been 16 outs. So what I need to do is come up with a way of taking a base on balls and assigning it to the A, and I need to take a strikeout, and I need to assign it to the O. But once that's done, then the general logic for how this table or how those rows grow over the windowed functions is already set up, and those metrics, when you divide them by the denominator, those now become essentially independent variables that we can use to classify what the pitch type is. In this game so far, is this person batting 600, or overall for the season, are they batting 50 or 100 or 150? Is the player's overall performance up to this point with the sequence squashed together as a single individual point estimate? How does that maybe necessary? And I don't know if it does, but it's one of the features that we'll include in the data set itself and in the analysis. Does that change which pitch gets thrown and how fast and where it gets thrown to? So I think that's it for now. I'll work on a couple more things. I'll get the strikeouts handled a little bit more intuitively, I think. We'll get the walks, the bases on balls added into the A, and then I'll do the same thing with these pitch counts. We will keep track of the pitcher's strikes. We'll keep track of the overall pitcher's balls, and maybe hits and maybe outs as well across their game, across their season, and then maybe across their individual counts starts. And then once those two are done, then I'll start getting in, and we'll do some analysis. One of the main things that I want to do next is plot what this metric looks like for a particular player, or essentially any player. Plot what that line series looks like over time. So like as the season progresses, do we see the percent of strikes that they see? How does that change throughout the season? And how does that change compared to what their number, or their mix of advancing versus outs are over time? Those are some interesting charts that I want to see how they play out. But I'm gonna call it for now. Thanks for Thanks for checking it out.